What up, and welcome back to the fifth part of the snake tutorial in x86 assembly. And as always, before we start, we have to correct something. Last time, actually a big mistake that I only realized in the ARM64 version, and that is I thought about the coordinate buffer, but in reality used the screen buffer. So if we go to the grow snake function and we go here down at the end where we remember we are adding the tail, we are simply taking the tail pointer, going one back, and that's how the snake grows. However, by doing that, we run the risk that we're in our circular buffer and that we pass the boundary in the negative and we have to wrap around to the front again. And what I did here is I used the screen buffer, but of course I meant the coordinate buffer. So let's fix that, coordinates. And I'm actually surprised that this worked, and I want my escape key, so let me check if the spelling is correct. So this seems fine, and we are back here. So now it's running. I don't see, the food is down here. We have our food and we can grow. So that is that. Now the next thing we're gonna do is actually I'm gonna change the sleep function now for a little bit. As of now, we used a busy loop, and that's obviously not a very elegant solution. What we're basically doing is give the CPU a lot of power, and it says go and do nothing, and do that very fast. So, and if you implemented that, you might have noticed that the terminal will tell you it uses an excessive amount of energy, and that's because we just let the CPU go brrr, and we don't want to do that. So we're going to use a very old Linux syscall called select, which still as a side effect has the ability to time out. And the way that works basically is in modern hardware for timing stuff, there is dedicated hardware that puts adds the number of seconds to wait to the scheduling, puts it in the queue, and then checks every, microsecond, nanosecond if it's time to pass it back to the CPU. And once it's the time, it passes it back to the CPU. And during that time, the CPU is obviously free to do other tasks. So it's much more energy efficient because it's dedicated hardware for the task, and it is also more precise. And now we have here a little bit of wind. Okay, so let's implement that. I'm gonna just copy the sleep function right here.
Settle down.
And then we're gonna comment it out and check our select. I still think it's a very good thing to start, with the busy loop because it shows you how primitively you can do it and it still works. But now the select syscall is a little upgrade. And it's even better for my battery. So let me check where the select syscall is. I wrote it down here as usual. So it's basically, we don't getting any input. We are just using the side effect of in register R8. So we need some struct here. And this has, well, on the x86 it doesn't have to be aligned. So is this part of the snake or not? Well, it's more of the playing field. So let's go here and say, what do we say? Timeout struct. And we're going to say it has space for, again, 10. Oh no, we're going to do this explicitly now. We're going to say this is this an A? I don't know what I'm writing here, quad 0. And because we don't really care for the seconds and we're going to go for the microseconds, I have no idea what I chose here. I might have to look that up. For now, let's go, 00A00. We will see if that serves us well or not. So let's go back to the sleep function. I paste this here. I'm gonna remove all of that. And now we don't need an address page. So we need the address layer Q. Now my laptop is here full of stuff. I don't know what happened here. Layer Q timeout struct rip in where do we need it? R8. So let's place it in R8, and RDE, RSE, RDX, and RCX, they all get a 0. So let's do that as well. Move Q0 into, oops, I didn't want this, in RDE, into RSE, into RDX, RDE, RSE, RDX, RCX. Oops. RCX and RDE, RSE, RDX, RCX, and now we have to make, what's the syscall number that are we gonna do again? Our sys select, and that is 5D. So let's place that right about here with our other syscalls. Oh, do we have this? Okay. EQ sys underscore select, and this is gonna be 0x 2, 1, 2, 3, 4, 5 zeros and a 5D. 1, 2, 3, 4, 5, and these are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. A little surprise here. 1, 2, 3, 4. 1, 2, 3. It's 4. Yeah, that makes more sense. So that is that. So let's go to select here. 1, 2, 1, 2, 3, 4. Yeah, that's correct. So we are in select, and then we have to do the syscall. Layer Q mnemonic timeout struct. To 7. Timeout struct is here. I have to do this maybe. So we have this ready. So I'm going to layer cube dot. Is there a dot? I don't see a dot. Okay.
Somebody took, whoever found your card spent the $20, you need $20. You're welcome.
So let's do this. movq select into RAX, obviously. RAX. Now let's do that. And now finally, what is unexpected token? Maybe we should, maybe the number is there a dot here? Quad. No. Let me check the number that I had here. 1 second. That's 222. It's all. I have here a completely different number. That's maybe it's just I don't need the quad here. Okay, and that's a little fast, or it's not working at all. So what number do I have there? 8,000. 8, 1, 2, 3, 4. 3. Okay, let's test this. And that's better. So it is working. And we can still move around. And maybe that's put here a 9. It's a little smoother. Let's do an A. That's like all of this nonsense. Okay, for now that's fine. So now we have a more efficient sleep function. And now we come to the main, well, almost the main part of the video, which is obviously to create the hit detection. So at the moment we cannot, if I find a food here, we cannot kill ourselves. Well, even skill issues. So now we can just go through it. So how do we fix that? Well, if we have the head and we have all the coordinates in the coordinates buffer, I'm calling it not the screen buffer, it's the coordinates buffer. And all we need to do is take the coordinates of the head and check against all the other coordinates in the body. And then if they're the same, we obviously hit the body. We need to do the exact same thing for the food, because the food should not spawn within the body. So if it spawns in the body, we generate a new one and spawn it outside of the body. That's the exact same function or the exact same mechanics. So what we're going to do is we're going to write a helper function. I don't know where to place it. No, it doesn't really matter. Initialize snake, print playing field. Oh, I wanted to do something. Let me do that. 1 second. Let me CP this. Now back up. x86. Yeah, I wanted to do that. So kill that. Okay, so let's go here to anywhere before move snake, and let's implement is element in segment of snake. In segment of snake. And now we get a little bit into coding, so I'm gonna do the prolog push q rbp move q. Which direction are we? Move q rsp into rbp. That's the direction. B, oh god. G replace as F, B replace stack pointer, pop Q, RBP, and return. So now what do we actually get to the function? The first thing we're going to input is the address of the element that we want to detect if it's in the snake. So this is always here RDE, address of element to check. Then we have RSE, which is going to get the starting address of from where to check. Starting address. And RDX is going to get the end address. The point here is that if we are using the function for the food, obviously it cannot spot in the head, while the head is only from the tail to head -1 in the coordinate buffer. We cannot check head against head. So we need to specify what element to check and from where we start and where we end. So that's the idea. Okay, so far I haven't thought any further than that. So in RDE, we have our elements. Do we want to put it on the local stack frame or not? Well, the first thing, remember we have the pointer so we can get the actual element, the coordinate, no, the address of the coordinate buffer. So movq, I'm willing to check my notes here a little bit. 1 second. Segment RNE. Yeah. Okay. The first thing we do is we place it on the local stack frame. So we're gonna also make space of it. Subq 16 on the local stack frame, and we're gonna store -8 RBP into, nope, we're gonna store other direction. We're gonna store RDE. Well, there I stored RDX and RDE, so let's do that as well. RDX X here. And let's do RDE in 16 RC. Can I place this maybe better here? RC, and now we have the address of the element is in RDE, and now we want the actual coordinates of the element. So we're gonna move byte, whatever. Let me just get into this here 1 second. Move byte 0 from RDE into allo, and move. This is 1 byte apart, so we're gonna move that into CLO, and this needs coordinates. So now we have, if we had the address before, so if it's the head, we have the coordinates of the head. We have to be a little bit careful because I have the head, we have the head pointer, and the food, we have the address of the food, and the address of the head is not what we want. We want the pointer. So we get the coordinates here of the head in AL and CL. So this should be fine. And now we need the tail. We need the tail. And yeah, let's do, we have the tail in starting address, end address. So I assume that RSE holds the tail pointer and RDX has the head -1 pointer. So we are looping from the end of the snake to the beginning of the snake. So let's do the segment loop, and then we're gonna eventually branch to segment loop, and we need the end. We need the end. So we need the end is the RDX, A low and C low. Also, we need the coordinates RDX is pointing to, and those are the things we're gonna compare or not. We can also use the pointer. I think the pointer is probably better, and we always move forward in parts of 2 until we hit the pointer. Okay, let's do that. I don't want to check this here. RDX. So RDX is our end. So let it move it back. Move Q -8 RBP into RDX. Actually, it should be in there, so it doesn't really matter. And then we compare our SE which is the starting address with the end address. So we are looping actually from the address behind the head here to the end. No, that's not true. A starting address is the tail. So we are doing exactly what I said. We're starting here, and we will increase the RSE pointer until we hit the RDX pointer. That's where we stop. So we can maybe I just write this here. We're going to add q %2 to RSE. I think that's pretty safe to say, or not. REX? Oh no, that's not. Yeah, that's correct. The only thing we have to do at modulo. I should like be a little more tentative here. So add Q2 to the RSE. What's the next step? We need the coordinates at the point. So RSE, do we need RSE? Once we have the coordinate, we don't really need it. Right, so here we're gonna write, don't forget the mod. Don't forget to mod. But basically we add the two, and then now we're gonna compare. So let's move byte 0 from RSE into whatever. A, C, D is occupied, so what do we use? R8 and R9. Okay. Our 8 byte and 1 R9 byte. So now we have X and Y, and now we're going to compare byte A low with our 8 byte, whatever it is, and jump equal, if jump equal next segment. So we're gonna do next segment is gonna be here. If the x coordinates are equal, we're also gonna check the, what happens here? If the x coordinates are equal, we're also gonna check the y coordinate. What am I doing here? Okay, we jump to the next segment. I can't see again. Otherwise, we're going to compare byte C low with our 9 bytes. If they are not equal, right? Jump not equal, and if they are not equal, we're going to also go to the next segment. And if, well, what am I doing? Escape this, write it down, compile, complain, invalid operand, RC into R byte low. No, you want a % sign, which is totally fine, and you deserve a % sign here. CMBB, compare byte, and branch segment loop is not a thing at all in x86. Okay, so now we have that part. Let's assume we are still within bounds of stuff that's working. So if we compare the x coordinates, if they are not equal, we bail. We compare the y coordinates. If they are not equal, we also bail. But if they are equal, we're going to say move q 0 into RAX. that means, oh no, we put a 1 here. It's true, we hit the coordinate given, or the coordinates at the address given matches with one segment of the snake, and we return simply 1. And then we're going to jump out of the loop to the end here. And this should be fine. Okay. So this is the successful part, and jump segment loop. Why do I have no end segment loop? So here's the end segment loop. If we really reach the end here at one point, we have our condition not, we have it here, but we have not the branch condition. So it's a little chaotic, I'm sorry, but we have a lot of other stuff to do. So not a lot, but I have to get my head into this part. So end segment loop. If we are here, we're going to move a 0 into RAX. So we didn't interact with any part. We exit the function and it's false. So the function name is element in segment of snake? No. So we are good. If it's true, we have to do something. So here we are checking RSE and RDX and jump equal to end segment loop. That's hopefully the right thing to do. And then here we have to mod. So what do we mod here? We are adding the 2 in RSE. RSE is, let me confirm this, modulo range is our function somewhere. Where is it? Here. RDE has the, RSE has the lower bound, RDX has the upper bound, and value. RDE has the value. So going back here, we have our value actually in RSE, so we have to move. Couldn't have done this better maybe. RSE into RDE, then layer Q, the lower bound is the coordinate buffer. Layer Q, the address of it. Coordinates, rip into RSE, and layer Q, where's my A? Layer Q head, rip into RDX. And then we're going to call modulo range, get the result in RAX and move it from RAX back to RSE. Let me confirm that here. RX to RSE, head in RDX, that's correct. Coordinates in RSE, RSE to RDE at Q2. Seems legit. Jump, end is element, we move a 1 there. Next segment, 9B. Well, it looks, this doesn't look right. AL1 is 0 here. This does not look right. No, what is this? Why are these two the same thing? What do I do the same? RSE, RDE. Well, this looks like, what the hell was I doing here? RSE and RDE, they have to be both the same. We are at the beginning, RSE, and why am I doing this? Here, this makes no sense. So let's do that exactly once. Well, if I know where I was. Now I have something my. Let's do that exactly once and within the loop. Right, here is our coordinate. What is RDX is the end. RSE changes. RSE never changes in the loop. A 15 is also no value for a computer. So we have our RSE, we have our RDX, and here, where's our 8? This is RSE. This is RSE. Where's RL and A low? Did I just delete? Could I just not read? Yeah, I could not read. So this is RDE, that's correct, and RSE is the value. So RDE is the address of the element we want. AL and CLOW get the coordinates. Then in RSE is the starting thing. Every loop iteration, we get the new coordinates. We update the pointer and we compare the pointer. So this, don't forget the mod didn't do that. So let's check that. Okay. Unfortunately, we didn't use the function yet. So let's change that. You're gonna write check vital status. Did I status? Did I name it like that? I cannot even use that here. Check vital status. That's right. So let's do the relaxing part. Push Q RBP, move Q RBP. We're walking through the function in a moment. The moment when we have our segfault. That's the exact moment we're going to do that. So we're going to do that. I don't know why I did that. We're going to pop Q RBP and we're going to return. Okay, so what do we need to do now? We have to have a flag if our snake is alive. So we're gonna put this somewhere here. Head, tail, direction is alive. It's gonna get a byte, and at the beginning it's gonna be alive, so it's gonna true. And then we need to check that somewhere. So let's get to our game loop here. Do we do here? It doesn't really matter. So we're gonna say move Q is alive, rip into RAX, and then we're gonna compare, no, we're gonna move the byte in low, and then we're gonna compare the byte to 0, low, and is it alive? And if they are, now if it's 0, or we can say, is it alive is the question. If it's true, we keep going and jump not equal whatever, and game loop. And we don't want this here. So we go down here. Let me, oops. Let's check that. So here we have our snake. It's the alive. And now we're gonna go here. If I place a 0 here, what happens? It immediately exits. Yeah, so let's try it again. make it exits, we chase it to a 1. So we start with a living snake, and now the living snake is working. Let me make sure this is stopped. Oh, this looks like a long snake. Why was that so long? It's all okay, yeah? There's more food. We have a problem. 1 second, we have a problem. Put is alive. Where is food is served? Food is served. Let's check that here. Compare byte. Move byte in IL. Put food on the table. Move byte 1. This looks correct. And move byte is 0. Food is served. So the timeout struct is the timeout struct here. RDE, RSE. Let's move that. Let's move that down here for a moment. Now there's still food, and it's coming after time. Okay. So food is served has to get changed, and it can really only be changed here. So that's unnecessary anyways. So let's check this here. Where's the food layer? Q move byte. That's all fine. Storing X and Y. Food is served. A low, B low. I don't know which one is which here. The comment is definitely wrong. And the snake grows. So something is off. Grow snake. This here looks wrong. Okay, I corrected that. Well, now it's spawned in the snake. It's okay. Okay, so I think I changed that during the recording here. So now it is supposedly changed again somewhere in the snake. So let us discover the food right now, because I'm getting a little paranoid. There was the food. So now we have the next one. There it is. It still seems to be spawning in a weird way. Grow snake, compare IL with I'll do this. And food is served. This here is not equal. We compare it with AL and CL. This whole looks, what is going on here? Head, here's the head. R is E. Okay, that's the head. We have ALO and CL. This is not, did I change that? RDE. I changed something in grow snake because I thought it's our new function. It's still not correct. Okay, 1 second. We have here the head pointer. So this is the X of the head, this is the Y of the head. This is the X of the, yeah, this is all, this is 0, 0, and this is 1, 1. Yeah, okay, I fucked up. Well, the reason I fucked up here is, let's go through it 1 second. Here's the head, and we have the food, and we are checking is X of food, which are both the 0 coordinate, the same, and if they're the same, if they're not the same, we're going to continue, and here we're going to check if the Y coordinate's the same, and if they are, if they're not, then we continue, otherwise we do what we have to do if the food is eaten. All right, good start of the day. So where is layer Q? No, where is our segment part? So that's the segment part. Here's RAR low and R bytes, so this is what we have to check now. So check the vital status. What do we need? We need the head, and we need not the address of the head pointer, but we need the address of the coordinates. So we're going to move Q head rip into RDE, and then we need the start address, and that is layer Q coordinates of or rip into RSE, and now we need to subtract 2 from the head pointer, so sub Q2 of RDE, and we need to mod that as well. And how do we do that? So let's do that first. So we take the head pointer, we're gonna subtract 2, and this has to be in RDE, and the lower range is still RSE, and the upper range is head. Head rip into RDX. So now we have everything set up, I hope, to call modulo range. And now we should move Q REX into RDE, because RDE now we're going to call the segment. So let's run this function. Let's put this in our game loop. We grow the snake, we put food on the table, maybe here. Check vital status, and let's see if we crash. Okay, so far at least we don't crash. Just do a little bit of mod, do a little bit of sleeping. We still can eat and grow. All right, and let me check. Just getting a little paranoid. Okay. Well, I guess I can always do that. Okay, this cannot happen in the real game because we would die at this point, right? So just to be clear. And also, we are eating at the correct position. I should have mentioned that. In the last video, I think I was a little confused about if we are 1 coordinate ahead, or we had the head in slow motion and we had the coordinates, and what we saw in the previous frame was that the head was 1 coordinate before the food. And now I already said it pretty much. The frame we saw was the previous frame, because the frame always gets printed at the end of the loop. Okay, so we are not crashing the thing. So is this correct here? So now let's say we have, let me check this anyways, head RDX, slightly different orders, coordinates in RSE, RDX in RDE, move layer Q head. Okay, here, no, well this is better, we use movq. So here I use layer Q and indirect, that's, I have to correct that. Movq gets the direct value, this should be fine. And now we call modulo range. Head, tail and head. RSE and RDE, we have our RDX. Oh yeah, that's correct. So what we did here, we have the head pointer and we are subtracted 2. So we are not at the head, but we are one element before the head. And that's the end of our loop. And we start the loop with tail. And I think that's RSE. And what the actual element we are checking is the head. Rip in RDE. RDE. Is that correct? Head in RDE, yes. So now we're going to call the function and then we're going to step through it because now we get our seg form. Is element in segment of snake. Well, it's running. Oh, we have a bus error, even better. Okay. I don't even care, we just run it. Where are we? SBBB. Okay, backtrack. I don't know where we took a wrong turn here. Call is element in snake. Let me check in segment of snake. So we're gonna do, you're gonna just step through it. What is the batteries? Oh, we are fine here. Oh, okay. Check vital status. That's really what we want to do. What? Well, did I copy this correctly? Where is it? Check vital status. I'm gonna take this. LLDB snake break set address. A little weird stuff here. Modulo, no. Please jump over it. Register read RAX. Snake plus 6. I believe that. And here we go. Register read low. So this should now be 19. Let's check. Oh, I know. I think I know what's going on. This is screen buffer. Let us do something. I think I want to XOR Q RAX here. XOR Q RCX. And maybe we even need to do that with the R8 and 9. Check if I did that. Element in segment. I OR them out. I do not OR out. Why does RDE here change? We are calling something here. We're not really, we are calling modulo range. So RDX here might change. So we should do, okay, wait. Let's do this here first. 8, 9, and 9. So let's do this. Still a bus error. However, I have here, I store this, I have RDE and RA and RLow. I zero out this part. But I was a little bit careful here with the RDE. So let's do that here. Let's assume that RDE changes and RLow and RCL as well, because they are used in the mod function. So we are loading this here. This is where we kept RDE. So let's do that into %RDE. Still nothing. So we have to step through it. Check vital status. LLDB snake. Okay, we're here. So register read RAX. Snake +6. Register read. Let's go. Register read RSE. Snake +2. Register read RDE. Snake +8. So this makes all sense, right? We are 2. We have 6 is the third segment, and 2 more is the head. So this seems okay so far. Now we go into the function. We have here RDX is the address of the end. That's correct. Register read RDE. That's the address of the tail of the beginning for the loop. We are zeroing out REX, so we get register read REX here is 19. This should be the X coordinate. Then register read RCX. This is 7. This looks good. So now here goes nothing. Register read RSE. Register read RSE is snake +2. Register read RDX is snake +6. 4, 6, so 3 segments to check. Sounds reasonable. Register read RDE, snake +8. Stays the same. 19 should also stay the same. RCX stays the same. We register read R8. Check this. 16. This is where the food is, or what are we checking? No, where? Register read R9, 7. So this is where the tail. 16, 17, 18, 19, 20. Does this line up? What is register read RAX? The Y coordinate 19. So we have 16, 17, 18, 19. 16, 17, 18, 19. 4. But we are checking the head, or we are checking the head -1. So, well, register read, it's not unreasonable, right? Register read R8, 16, they are not equal. So we're going to the next segment. Register read RSE, snake plus 4. That's correct. We're gonna go modulo, register read RAX, register read RAX, snake plus 4, register read RSE is now snake. So we are back here, and now we have REX used, and that's why we need to do the comparison. So that's also fair. What apropos? We want to step. So we are not equal. Let's check REX. What? Read RDE. Register read RDE. Snake plus 8. Register read RAX. Y. Step. Register read RCX is 7. Register read RAX. That's not correct. Why? You should have it loaded right about here into RDE. R low, C low. Why is here not RAX correct? Okay, R8 byte. Where's the read R8? So now it should be again the coordinate, and it's not. So let's check. Let's actually remove that here, and let's just check this here. Just want to make sure for the moment. That's not what we're doing wrong here. Object dump minus D snake. Let's go to the vital status right about here. Breaks LLDB. Break set address, and here goes nothing. Object dump minus D snake. Check vital status. Where is it? LLDB snake break set minus address. Here we go. Here we are. So here everything is still fine. Modulo range, that's where we never want it to be. We want to be right here. So here and now a screen buffer. REX, at what point are we? We are moving it out. We are in the loop. We have register read RDE, snake plus 8, snake plus 8. Step register read RLow, register read RAX, 19. Okay, register read RCX, 7. Register read R8, and register read R9. Okay, there's 0, and now this should have changed, 16, and 9 should also be 7. That's all good, they're not the same. We're gonna do some mod work. we stay the same, and we jump to the beginning. RDX, snake plus 6, register read RSE, read RSE, snake plus 4. Do we load? Yes, we load the element before, so that's okay. We're doing this. And now is the question, if RX is 19, that's correct. And RCX is 7. So we are here. Step, step, register read R8, register read R8. Oh, we are not there yet. Now it should 17, register read R9 is still 7, register read RAX is 19, and 8 is 17, okay? So this looks all okay. So we should move we exited. I was too soon. Why did we exit? We should have had we add here segment loop. Let me check this part here. No, yes, here. Now where do we call it? Here. Track 2 from RDE. Why did we exit? So let's run this again real fast. Let's go here. Register read RDE. We start with snake plus 8. Our SE is snake plus 2. That's the beginning. That RDE is our head. And 6 RDX should be snake plus 6. So that's all fine. But why did we exit so early? Let me check here if the recording is still okay. Yes. Xorg. We have the jump here. Do we change RSE? Let's next register read RSE. That is now snake. Okay, no, but register read RSE. Snake plus 6. That's still fine. Register read RDX. Snake plus 6. RSE. Snake plus 6. So we exited. Seems a little early. 2, 4, 6. We have we have to check that element. Regardless, that's not a reason to crash. So end segment, move Q0 in RX, yes. Go here. So here is something. No, I think I messed up here at the beginning when I was confused. So we have RBP, and we move the stack pointer in the base pointer when we really want to move the base pointer in the stack pointer. So that's a thing, but I think we are still exiting the loop prematurely 1. Nevertheless, let's see. Well, we are not doing anything yet with it. We are running it. So, okay, let's assume that works. And go to vital status. Check vital status, and we have the element in the segment of the snake, and if REX comes back as, well, we ask is the head in the snake. If it's true, we're gonna say it's not alive, otherwise we're just gonna bail or leave the loop. So we're gonna I'm not doing anything. Why is this not aligning? Okay, I'm sorry, we're gonna get this. We're gonna compare Q 0. Do we check if it's alive or if it's dead? If it's false, it's still alive. So we're gonna compare 0 with REX. I'm gonna stay, if it's equal, jump equal, still alive. Still alive and kicking. And kicking. So otherwise, we're gonna move Q. We have x86. We have this nice option. We're gonna move Q 1, 0. It's not alive into is alive. Alive. RIP. And that should end it. So how do we test this? Well, we first test this by giving us a longer snake, somewhere initial length. Let's make it 11 or 14, why not? So it's long, and with that, that works. So I still think we might be off by 1 there. But that's already good. So that, well, we are at least at the end. If we are off by 1, it's the part behind the head. All right, so this all works. And now we're dead. Good. Well, at least something worked. What I think is alive. No, is element in segment of snake. We could. Where is the comparison function? So what if we do that 1 into REX, jump next segment, and then move a 1 into RX. What is the 1 here? Oh, that's the truth. Jump next segment. This is next segment. So what if we do this right here? Well, that still works. This also works. So for now, we're going to keep it that way. I think that makes more sense. And this seems to work. So now that we have our is element in segment of snake function, we can also take care of the food, because as of now, the food can spawn anywhere within the snake, and that's not what we want. Obviously, we want to check that if the random numbers generated are within the snake, we're just simply gonna regenerate new numbers. That's the idea now. So we're going to reuse our function here. And I want to check a few things. Segment loop, there's a little much that I do here. Let's delete the XOR right about here. ALC low, this is not necessary. Let's remove that. Right, because we have here, we are clearing it, and then we are loading it from RDE. We are clearing 8 and 9, and then we are getting it from the frame pointer and the loop pointer, and the loop pointer updates somewhere down here with the mod function. Now I have here I'm on the microphone. That's all fine. Okay, so now let's go. Let's keep cooking. Put food on the table. That's somewhere the function that we want to have. So where is it? Right about here. Food is served. And if food is served, we jump to the end of the function, and otherwise we're gonna be here. And now we're gonna call this, I think I called this keep cooking or something. Let me check my names here. First of all, get cooking. That's what I called it. Okay. Get cooking. And in the isAlive function, I wanted to check that real fast. Somewhere it has to be. Put food on the table, get cooking, check vital status. If it's and check vital status. Oh, no, still alive and kicking. Still alive and kicking is okay. Well, we have here two loops, two labels. We can remove that. Still alive and kicking should be fine. Okay. So, where am I, why am I, and what am I doing? Get cooking, that was our goal now, get cooking. So here, let us check what we did last time. We have the 1 in RDE, we have the height -1 in RSE, we get a random number in that range, and then we move it on the frame pointer, on the stack frame, on the local stack frame, and then we do the same for the Y coordinate, move that on the local stack frame, and finally we get our food and place the coordinates in the food variable. Okay, so before we're gonna do that, wait, let me check what else we're doing. Okay, and once we have the food coordinates, we're gonna load them. Well, we put them in memory, and then here we place them on the field. Before we place them on the field, we want to now obviously check if we accidentally generated an element within the snake. So what do we need? We need the element of food. So we placed here, we have it in RCX. So right about here, I guess, is my feedback on the keys here works not good. So layer Q, and that's the layer Q food rip into the element we want to check, which is RDE. RSE is the coordinate buffer. Layer Q, no, yes, it's the coordinate buffer, and we are checking it basically from head to tail. So let's do movq tail rip into RSE and the head into rdx, RDE, RC, RDX, and then we're going to call is element in segment of snake. And then we say, well, it comes back 0 or 1, it's either in there or not, and so we're going to say compare Q if it's true. So let's say if compare 1 with RAX, we're going to say jump equal to get cooking. And I think keep cooking is cooler. So let's rename it to keep cooking. We're gonna keep cooking until we have cooked something that is not in the snake body. That's the idea. Keep cooking, and otherwise we place it on the table. So yeah, is that all? Well, now we have nothing on the table. Great. So call is element in segment of snake. Okay, so I guess we are using all of this. So we have here the coordinates of food. So we can do this and copy it down here. So we're going to load the address of food. I don't want to store anything. I just want to have I guess in RCX we have to check what we used here. RAX and RDX, I guess. No, it's like, okay, 1 second. We have RDX is what? RAX minus 16, this is here the x coordinate. Yeah, but we want RCX is the food. We want to store R low, and then we get minus 8 in RX and store this. So we are very clever here. Let's remove that. We're getting our CX, but the real question is where do we want to have it? And the answer is we are multiplying by Y. So we want the Y coordinate in Rx and the X in here, the X in RDX. So let's just do that. So move Q, move byte 0 RCX into whatever I said, D low, and the Y coordinate in A low. There's food, and there's food again. So now will it spawn in the snake? Well, it shouldn't. Doesn't seem it does, but let's keep going for a moment here. Get this. We have this. Could be a little bit faster, but we are going to take care of that in a moment. What time? 1:20. That's okay. We are still on track. on track, on target, and there's food, so it didn't spawn in the snake. Up until now, we could have been lucky. No, we're dead. But I think we're good. Let me check the camera 1 second here. I think we are fine. Let's get this. Let's get this. No, oh no, there it is. I just can't see it. All is good. So I think we're fine. Here we're also fine. Fuck. Batteries. Okay, and battery here is 43%. So now comes the part. Oh, almost forgot. So up until now, let me check. I had a list, notes. Correction of coordinates did that. Change in sleep function did that. Write element and segment. Write check vital status. Check put foot on the phone. And now check escape key. Exactly. Almost forgot that part. So what we're going to do now, up until now, I press Control C to exit the function. But what we really want to do is go on the correct control path and say we exit once I press escape. That's the idea. And exit the function gracefully. So how do we do that? We are going back to Control Snake. We're doing our first syscall right about here. And then we are doing what? We are taking the input key. Remember, we are reading in only 1 byte. So assuming we are pressing an arrow key, we get escape something, but at the moment we only get escape. And then we are checking it here against escape. So now what we're going to do, we're going to move a 0 and control. So if it's no escape, we are going to bail out immediately. Otherwise, now we're going to move byte, a 0, into input. Where do we move that? Input key +8 rip. Is that an instruction? So because that is to keep track of any residual, because if we pressed an arrow key, you can imagine you have the memory address and you have the escape and the previous arrow address still there, but now we want to check if it's only escape, so we have to erase the previous arrow key press. So that's what this thing here should do. And then we're going to do the syscall. We have AL. And here we could compare byte, a 0 with our low, and jump, jump not equal to continue playing. So let's do that here. Continue playing, and if, does this still work? So now if I press escape, nothing happens. But now what I want to do here is I want to say movq is alive is false. So we're going to move byte a 0 into is alive rip. And now if I press escape, we get a segfault, exactly what we want. Okay, what is there happening? Is alive, continue braying, is alive. Maybe we should here jump to end to the function here. End controls. End controls, we have also 2 labels there. That's not nice. We're going to do a cleanup on the GitHub. That's not the point. Jump here. No colon. We have this here. Now if I press escape, I get the segfault. I don't want a segfault. Okay. LLDB, snake, run it. Failed. Memory failed. Yeah, okay. But where? Is alive, rip. Move byte 0, jump if it's compare byte, if it's not equal, continue playing. Let me check my notes. Why did I bring them if I don't use them? Wherever I am. Control snake function. 1 second. Whatever I did. 1 in C low. Is alive. Compare byte 0. Oh, first of all, input key plus 1. This here, input key plus 8. This is stupid. I don't know if that's the error because everything looks different. Let me escape it. Well, that works. Maybe that was just it. Okay. Well, everything here is different, but you can still control it. So do we get this in half an hour? Well, we have to. So this was everything we set out for the Easter special, which is now a little past its time. Nevertheless, I think that's the core game. We have the food, we have to grow, we have control keys, we can exit it. And okay, I need this in a moment, so let me close that. Let's check this here. So what did I change? I had here the 0, I zero it out, I XOR the RAX, and this was all C in my notes. So let me check the RAX here to C. C low, continue playing, otherwise we move an is alive a 0, jump to the end, and if we continue playing, we do what we need to do. This is a thing. Okay, I changed something I shouldn't have changed. And Arlo. And controls. Low. Oh, this is, I'm just changing the spec because I used R here, A here, and in my notes I think we coded that fairly free. So let's just go back to A. It doesn't matter. Okay. So that's all we had to set out. So obviously, because this is an Easter special, this is what we had for the Easter special. So I have my final Easter bunny. And we're going to go here on the last stretch of this part. So let me kill this bunny. And I also have a dry mouse because it's warm. So chocolate will certainly help. It doesn't matter. Has to go. So as much as I love this, and this is the core game, and I think everything from here can be a little bit like code obfuscation, there's one thing I'm not fond about, and that is the fact that if you run the game on the x86 and the code in the ARM64 assembly, they both will be different. They will run at different speeds. So if we were to race against each other, right, then if you have a slower computer, it's easier for you. So we can't have that. So why is that? Because the select key, if we go to the main loop here, right about here, the loop starts, and here we print the frame. And the code, even though we wrote the same functions, all of this code is different on the x86 and on the on the x86 and on the ARM64. x86 ARM64, yes, saying it correctly. So how do we counter that? How do we make sure that they are both the exact same time? And that's actually a little bit of a head scratcher. The first thing I did is I initialized the loop, so I set a timer, get time of day, used our function, set a timer at the beginning of the loop. Then before printing the loop, I checked the time again, and I said we are supposed to take a timeout of, I say 500, let's say 500 microseconds. It's actually a different value, but for simplicity, 500 microseconds. And then we said, well, the code already executed like 15 microseconds or 8 microseconds. So I subtracted the 8 microseconds from the 500, gave it to the select syscall, and timed it out accordingly. Now this works fine for about 2 minutes, 2-3 minutes, and then if I line up the ARM64 version and the x86 version, then they slowly get out of sync. And the reason is because what we are effectively doing is we are timing the code from the beginning to the loop to print playing field. We are trying to equalize it, but everything to set up the function itself we are ignoring. So the assembly instructions are still different. So there is a little a way that's a little more involved to correct that. And it's a little unnecessary. No, it's not unnecessary because we want to race, but we have to check that. So here's how we're going to do it. We know every time we print a frame that one frame has passed, right? So we can count the frames. So every time, so I'm going to outline what we're going to do now. Every time we print a frame, we're going to count. First time, second time, third time, fourth time, fifth time, and so on. And then we're going to say, before we start the game loop, we're going to say, okay, we're going to time it once. We're going to set a timer, and we're going to set the frames to 0. And each time, after printing, we're going to check the time again and say, okay, we are now 18 frames in. So we should have been 18 times 500 milliseconds should have passed at the end of the frame. And then we're going to measure the time again, and we're going to take the projected time versus the time that we actually measure and adjust the timeout. Okay, and there's a subtlety here that the frame ends. What we're interested in is the end of the frame, because that's the timeout. We are projecting the timeout, we are measuring the time, and adjust the timeout. Because once the select key is ended, the select key comes back, we immediately clear the screen. So what we have to take care of is that we are talking about the end of the of the frame. And then, because we are counting the frames, every time we do that, we are taking into account the mistakes we made in the previous calculation. And this will keep the two snakes aligned. I tested it for about 20 minutes and I think it should work for longer. I'm not watching a snake in parallel for more than 20 minutes. So that's the game plan right now, to adjust the timing. And well, I would say here goes nothing. Let's go. Well, the first thing we're going to do is initialize the timing somewhere. Get time of day. I'm going to say set initialize timer. Initialize global timer. Push Q RBP Let's do this right, otherwise we're debugging for another 20 minutes here. Pop Q RBP and return. So the first thing we need to do is have a struct for that as well. Timeout struct. We need set global timer struct. I want to check my notes on that one because I have names and I just did that, I think, yesterday. Let me go down here. Nope. I have here some stuff from previous things. So we are gonna time start frame and time end frame. No. Let's go here. No, that's the old version that I just mentioned before. I have here still both, so I have to be a little bit careful. If I think about it, I will place this at the end of the video or in a hidden video where we can watch 20 minutes two snakes go in parallel and see them go out of sync. But yeah, let me check that. Count frames and frame start time global. This sounds more like something I would name. Frame start time global. And that's because we are only initializing the time once for the whole loop, and we are not resetting the time each loop, because that's the way to get in trouble. Punct quad, set it to 0, and then we need a frame count somewhere. So let's do that here. We have to be careful not to get this out of, no, on the x86 it's fine. Frame count is also a quad, and there's no real risk in overflowing. We're talking years, many years. I don't know how many, but too many. So frame count, that's what we're going to do. We're going to frame start time global. And now we're going to initialize timeout. Global timer, initialize timeout. Timeout. None of this is good. And initialize timeout. So now the first thing we're going to do is move Q0 into the frame, whatever it's called, count frames rip. No, I didn't name it that way, so we have to check that in a moment. And then we're gonna say layer queue this, no! Okay, where is my name? Frame count. Frame count. So here, it's this into, and that's now using the get time of day syscall. So we're putting this in RDE, and I should simply be able to use this all here. And now I have count frames. Why is this not frame count and count frames? Whatever is better, nobody knows. Initialize timeout, invalid instruction. Please tell me you just want a colon. Rix has never been a register. Which one is the use? RDE? RDE, RSE, RX. Let's put the initial length here again to 4. What am I doing? And initialize timeout. We're gonna call this immediately before the loop. Call initialize timeout. And I think I want to check that right now. Object dump snake. Where is it? Game loop initialize timeout. So let's check it out. LLDB snake break set. Oh, that's interesting. We have weird stuff going on. Initialize. What the hell was that? Call initialize snake. Call initialize timeout. RBP, RSP. Is this the problem? That is the problem. So the syscall destroys something that we need. And that is, which we are using RBX somewhere. Initialize playing field, this doesn't matter because that's long gone. What is this here? Initialize snake is also long gone. Move snake. Why are we using RBX and move snake? Let's not do that. Oh, that's a headache. This could be the reason though. And move snake. So 659. So 535 659. Substitute RBX with R11. Do we use R11? Not a good idea. Undo. Maybe 13. Also not a good idea. 14, 15. No. No, maybe we are using below and stuff. So, okay. Let's keep it that way for a moment. Game loop. maybe that's even not the reason, but I suspect it is. So movq rsp or subq base pointer into stack, that's all right, correct? Subq $16 into from RSP, and then we are just gonna move RBX, which is the suspect right now, into RBP, and then I'm gonna retrieve it right about here. No, that's not the reason. Why are we down there? So initialize timeout. What else could it be? That's a problem because I did not use RBP, I guess, in the original. Initialize timeout, RAX, RSE, that's all fine. 74, that's fine. Syscall is fine. PubQ, RBP, RSP, that's all fine. That's not syscall. Yes, 0. RDE is fine. RBP, RSP, RBP, return, RBX. So which move into and move it into RBX afterwards. So we should not change anything here. Let's try C as well. But otherwise, I don't know. CX. Nope. That's the height. Initialize timeout. But that's the problem. It's a little weird because initialize snake is finished at that point. We are here. I guess it's the move function, but that's also not really a thing. Call initialize timeout. Object dump minus d snake. Call I don't know where I am. Initialize snake. There is no timeout. It's because it's working. And now it should be not working. So the snake, you're overwriting something. Let's actually, maybe it's not the RBX. RDE, frame start, where is this? Frame start time global. This is not big enough. We need here something like space 16. Aha. Aha. And now, maybe this here was all premature. So let's do this. And we are just overriding it there in memory. Okay, we're back in the game. Literally. We still kill ourselves here. Not if we suck. So, yes. Okay. False alarm. Just another mistake. Good. So now we're gonna check the initialized timeout anyways. Where is it? Initialized timeout, right about here. LLDB snake, break set address. Here we are. Initialize timeout, register read RDE. So I just want to check that everything is there. Now here comes the syscall, and here's the time. So these are, remember, these are the seconds, and these are microseconds. Okay, so this is what we're gonna do now. We have it set, and now we're gonna go to our print playing field function, and before or after doesn't really matter. We're gonna move q a 1. No, we're gonna add q 1 to 1 second, and to count frames or frame counts. Count frames at rip. Does this work? I think x86 has that, yes. So we have count frames. We are here and we are initializing it to 0. And now we are adding 1 each time we print the playing field. Let me check my audio and camera 1 second. All right. We still count. We're still cooking. So now comes the hard function of the day. Initialize timeout. Set timeout. And end set timeout. But every function starts the same way. RBP. When I did the other timing, I tried to remove as much of the epilogue and prologue as possible, but it still got out of sync. So this is why we have to go here the extra mile. RBP and return. So what's the actual goal now? We have to get the frame count. We have to multiply it by our frame duration. Then we're gonna get the frame duration. Frame duration is in microseconds. So we have to get the actual seconds and microseconds. So we're gonna mod the duration, then we have the seconds and the microseconds, then we have to add that to the starting time. That's our projected end time. However, adding can again change the microseconds. There can still be an overflow, so we have to take care of that. And then once everything is taken care of, then we can get the time of the frame. Alright, so the idea is each time in the game loop, after we printed the frame, we updated the frame count, and now we're going to say how long is our timeout for the end. And so how long till we clear the screen again? So how long will the frame be from the start of the loop till the screen gets cleared again? and that's gonna be the time that we're gonna need to time out the function. So we're gonna call this all here. Call timeout, or whatever we called it. Timeout. Initialize timeout. Set timeout. So here wanna call set timeout. That's gonna be the thing. Okay. That's gonna be set timeout. Let's keep it moving. Do I take? Yes, we're gonna take the nodes. We're gonna need our stack frame pointer, so we're gonna subq. How much do we need? 32. 32 it is from RSP. And now we're gonna take the frames. Ready? The value movq frame counts. Is that the right word? No. Count frames. Frames. Is that the right word? Yes. Rip into RAX it is. And now we're going to use a magic number here. Yeah, for now we leave it as a magic number. This is our duration for one frame. This is going to go in RSE. And then we're going to divide that. So this number, the magic number, is going to be in microseconds. Okay, so we have the, well, this is, I'm ahead of myself. We're going to multiply, I multiply Q, our RSE, with RAX. So now we have, okay, I have to, this is a crucial step, is remember, we start the loop, we print the frame, we increase 1. So if we start at 0, we execute all our loop. Before we even print the first frame, we're gonna increase to 1. So all of this to the end should take 500, I'm saying 500 milliseconds. It's actually this value, AF00, which is like 488 microseconds or something. It's all written on the GitHub, yeah? But that doesn't matter right now. So we are printing at the end of the frame. But we are multiplying right before, after printing and before the end of the frame. So that's the mental space where we are right in now. So we just got the frame number. So we are in our first frame. We're multiplying it by AF00, call it 500 for now, and now we have 1 times 500 in that. And now we're going to take the maximum number for microseconds, 10 to the power of 6, micro, 10 to the power of 6, and that's in hex F4240. So we're going to move Q, think F0x F4240 into RCX. Maybe I write this here for the moment. This is 10 to the power of 6 microseconds. So now we want to take care of an overflow. So we have it already in RAX. Yeah, this is microseconds. We now want the seconds. So we're going to mod X or Q by the microsecond. So we will have the seconds, and in the mod, yeah, well, the division gives us the second, and the mod gives us the microseconds, the remaining microseconds. So we're gonna XOR out here RDX, RDX. And then we're gonna say div q by RCX. Or not. Div q RCX. So now we should have seconds in RAX and microseconds in RDX. Because this is the overflow value for microseconds 10 to the power of 6, and here is frame number times microseconds gives us the total duration of from the time we set our timer before the loop started to the moment we are in now in the game. And this will be in the first frame it's just 500 microseconds, but as the game progresses it's going to be seconds and microseconds, and that's what we're having right here. So now we're gonna add that to what? To the start time. So we need the start time somehow. Or I stored it first on the stack frame. That's probably clever. So let's do a stack. Put REX on the local stack frame and RDX as well. 16. And now we're gonna get the time we timed at the beginning. So we want the value. I want the microseconds and I want the seconds and the microseconds separately, so we're gonna get the address. Layer Q, whatever we call this. Frame, start, yeah, I'm not, where is it? There is it. Frame start time global. We're gonna take exactly that. Frame start time global. Rip into RE this. Into RE. So that's the timing. And now we're gonna get, oh, we need that also. We place that also on the stack frame. RDE. I did that yesterday. I still don't know why we need that right now. So RDE and RDD, this is RBP. So now we remember the frame start time global. We have it on our stack frame, but what we really want is now the seconds and the microseconds. And where do we put them? It's gonna be RAX, RDE. Okay. So RDE, movq 0, RDE, so that's the starting seconds before the loop even started, before, you can say before the game started. We are taking the time once at the beginning of the game, and that's the time we're talking about now here, the seconds. That's in RAX, then 8 further down, it's gonna be the microseconds. And now the same spiel for the things we just calculated here. Minus RAX, so let's take minus 8 RBP into, what? RAX, oh, I think RCX. And put this 16 into RDE and RSE. Is that right? Yes. So and here let's talk this. This is expected seconds passed since start. That's my chocolate. Did you steal my chocolate? A squirrel just stole my chocolate. It's there. Why did you do that? Why did you do that? It's right here. It's my chocolate. It's my chocolate. It stole my chocolate. That's like, that's Central Park. And now I'm eating it and I get sick. Oh yeah, keep this here. Let's see if it comes back. So, expected seconds passed. And this is expected microseconds passed. Microseconds passed. Since start. Yeah, well, this is like. So it's since start means we are not yet at the total time, right? We have the duration from the start to now, but not the total time. So this is now where we have to calculate the total time. So how do we do that? It's a fat squirrel as well. It's like out of shape squirrels. Okay, we're gonna add RCX and RDX. So this is seconds, RAX, and we're gonna add the microseconds. RD and RC, in which one do we keep it? RC and RDE. RC and RDE. So that's the microseconds. And now we're gonna check if the microseconds overflow. Yeah. So we're gonna compare it to exactly this value here. This is the. I'm gonna put this in an EQ at one point, but now we're gonna compare it. Compare Q. Oh no, we can't have that. We need battery. We need this with RDE, and if this is less or equal, and adjust microseconds overflow, adjust microseconds overflow. Now put this somewhere here. So if we have to adjust, all we need to do, these are the microseconds. So we got, if they are less or equal, that means they're negative. So we're going to shift it back. So we're going to add our magic number. Add Q this to RDE. That's correct. And then we're going to we have 1 second too much. So we're going to sub Q 1 from where our seconds here RAX. Okay, this should be fine. So this is the adjustment for the microseconds overflow and adjustment microsecond overflow. Oh my goodness, this is a lot. We have the projected time. Now let's store this on the stack frame. REX are now the seconds. RBP. And now we have it total. And what was the other one? RDE. Minus 60. So that's that. Okay, so now we have the frame count, we have the projected frame length when we want the frame to end. Right, remember we just increased the number of frames, we printed the frame, and we check in 500 or in AF00 the frame should end. What time is it now? And that's what we're going to do. We're going to now get the time of the current time. So that's the measurement that we're going to do. Layer Q frame end time into rip RDE, and that's going to be the exact same thing as we did here. Frame start time, all of this is going to be the same. All right, start time, end time, where's the end time? Frame end time, and I don't think we have that, so we need to have the start end time as well. So let's go back. Frame end time global is not the same. And frame end time global. So we have it. So now we have the time, and now we just need to check that the current time versus the predicted time. The predicted time is in the future, so the predicted time minus the current time is the timeout that we want. And I write this down in the GitHub, the mental model of when we take the time and that the frame ends at the end when we clear the screen, and when we take the time is crucial to understand in combination with the frame count. So, having said all of that, we are here. So now we put stuff on our stack frame again, or in our variables. You're gonna move Q24 RBP into RDE. 24 was, let me check this. This was here, the start time address into RDE. Move Q0 percent RDE. Okay, we're gonna need the start time X and Y, seconds and microseconds in RAX and RDE, staying consistent here, so we could just copy that from here. Yeah, let's copy it from there. 17980. This is this part. So we have everything back in our registers, and now we can subtract the future seconds from the seconds just measured. So that's RDE minus RSE. Well, here it's always the other way around, right? RSE minus RDE. So this is the one, then we check, is it 0? And here's a subtle bug I fixed this morning. This has to be greater, not equal. Because I had the x86 stall, and that's because we are now checking simply, did we hit a negative number, or so are we if we too close to the carryover that the subtraction goes in the negatives, because we don't care about seconds. We are never going to go into seconds. The timeout is never a second. It's always microsecond. We're going to clamp the seconds to 0. However, we have to check if we hit the boundary, and if we get into the negatives, we have to add again the magic number, or the full 10 to the power of 6 microseconds to get into the correct value. But we only do that if we are negative and not if we are 0. If we do that the moment we hit it exactly and we add 10 to the 6 to 0, then we are waiting and stalling a second. And I had the x86 stall randomly for 1 second, and that was the mistake. So here the jump greater is actually important. So jump greater for what? And then no carry. That's going to be no carry. So let's do a no carry There is no way in hell this is gonna work, but who else? So no carry, let's do the carry first. If we are in a negative number, all we have to do is add to RSE the magic number again, right? So add Q 89 jank, and I will eventually change the magic number, but now it's not RDE, it's RSE. And then when we carry, the first thing we're gonna do is we clamp out the seconds. We're never gonna wait a second in the game loop, so we're gonna immediately put this down to 0, whatever I called the struct. Oh, that's the, where's our sleep function? We did this today. Sleep function, timeout struct. This is what we need. I'm going to use the same. Where is our timeout struct now? Undo, redo here. I'm going to go into the timeout struct and with a 0. So we can maybe say here plus 0, and then we're gonna place the RSE here, RSE corrected or not corrected, into the microsecond struct right about here. And now all that remains is calling the select call. And we are not gonna call the sleep function. We are literally just copying this. Well, we need this here as well. And pasting this here. Because at this stage, we don't want any unnecessary delay in the function. 2, that should be, well, that's fine. For now, it's fine. Let's run it. RBP RDE 75. There's no comma here. We're not running at all. But we're also having the sleep function. Oh, that's not a timeout, that's a timeout. Ah, and we're not moving. Obviously, what's the battery saying? 3%. Object dump minus. Okay, let me call initial timeout. We set the timeout. Let us run through this here 1 second. RBP, RSP 32. We have the count. We have RC. We have the multiplication. We have this in RCX, we move out RDX, we divide, we store it on the stack frame, start global rip RDE, that's fine, 0 in REX, 8 in RDE, RBX and RBP, RCX, REX, RSE, RDE, magic number in RDE, microseconds overflow, up, microseconds overflow, add Q, REX. Here we have to add 1, not subtract 0. Subtract or adding 0 is stupid anyways, but if we overflow in the projection, we have to add 1 second. 1 second into RDE. Okay, yes. So we add the microseconds, we overflow, so we bring them back. So we have to subtract them. And then we add the second. So the microseconds become seconds. That's not it yet. So we have this part and adjust. We get the pointers. We have this in RDE, a 0 in RSE. Player queue, we want to move queue, frame end time, global, put this on the stack frame, minus 24 RBP. Come on. RBP, 0 in RSE, here's our syscall, 24, 0 RDE, RDE, minus 8 RBP, RSE, that's all fine. Sub RDE, RC, 0 in RSE, jump greater, no carry is here. We add the magic number to RC. Move 0, clamp out the timeout struct. And we're moving. So that's the time. So now let's check our magic number. So what I just overwrite the seconds. So we were waiting and we're done. Okay, so that was it for today. This was all and more that we intended for the Easter special. We're gonna do one more video. We're gonna add the scoreboard and we're gonna add a scoreboard so we can race. That's the primary reason why I wanted to have the two versions to run on the same timing. We have done this now. We're going to recap that in the next video a little bit. That was a thing we had to do. I hope everything is stored. Thank you very much for watching. Happy Easter. See you in the next one.